Pressure. Very well. Well, it looks like it's working. Okay, so let's let's recall that last week we proved that suspension is an equivalence for spectra. And we started proving that looping is, in fact, the inverse equivalence. And we did it assuming some diagram commutes, and we didn't check that this diagram commutes. So this was left as an exercise. Did anyone attempt to actually do this exercise? Well, looks like the answer is no. So let's briefly talk about that. So suppose we have a spectrum, not necessarily an omega spectrum or a CW spectrum, just a spectrum. Given x, we can do two things with it. We can shift it to the left by 1. Or we can also take the loop spaces of all maps. The loop spaces of all components, and if we have a map from xn to omega xn plus 1, we can loop this map and get the structure maps for this spectrum. And we started proving that these two functors of spectra are equivalent in the homotopy category. Namely, we constructed a map of spectra. Who remembers in which direction the map goes? Yes, so we have xn minus 1 to omega xn. Well, these are part of the structure maps of the original spectrum.
Sorry, I wasn't present last time. This homotopy category of spectra, is it with respect to the stable?
Yes, yes. So we localize, so this homotopy category is the same as spectra. With all maps which induce isomorphism of the homotopy groups inverted. Okay, so we have this map, and we want to check that this map, so these maps induce the map from x shifted by 1 to omega x, and we want to check that this map of spectra induces an isomorphism of the homotopy groups. Well, no. Okay, so this is the definition. Let's see what happens when, for example, n is 0. X1, or the zeroth component of x1 is the first component of x. So what happened to the spectrum? It got shifted to the left by 1. Okay, so and we want to see whether or not the map of the homotopy groups is an isomorphism. Well, let's draw the diagram. Let's see what happens when we take the pi n applied to both sides. Well, here I have the limit of pi n okay, so pi n plus I, and then I need to take the ith component of the spectrum x shifted by 1. So then I apply the suspension map, n plus I sigma n plus I plus 1 pi n plus I plus 1 of x I plus 2. Okay, so to get pi n of this spectrum, I need to take the limit of these maps over I. Well, what happens with the other spectrum? Well, I have pi n plus I omega xi. This is the ith component of this spectrum. I messed up the indices. So
maybe incidentally should have been shifted, like the square brackets by -1.
okay, let's see. So we have maps from xn minus 1 to omega xn. Okay, so here indeed in order for this in order for these to give us a map from here to here, we need to have a -1. So let's replace let's replace 1 by -1. Okay, so here we get -1, -1, and here we get just I. Okay, well, sorry about that. Pi n plus I sigma omega xi pi n plus I plus 1 omega x I plus 1, and we have this map, and we have this map. We don't assume that these are isomorphisms, just maps, and we need to show that this diagram commutes. Bless you. Very well. Firstly, my first claim is there is, in fact, an arrow going from here to here. So let's see where the arrow comes from. Basically, the square on the left is the suspension as a natural transformation applied to the map xi omega xi minus 1 to omega xi. The suspension is a natural transformation, and a natural transformation of these the natural transformation of what?
Of homotopy group functors. So, like on the left we have Pn plus I, and
yes.
on the right we should have n plus I plus 1. Also in the centered bottom we should plus I plus 1.
Yes, so we have two functors, pi n plus I of something, and pi n plus I plus 1 of the suspension of something. And we have a natural transformation of these two functors, which is the suspension homomorphism. So the left square commutes by naturality. What about the right square? Well, on the right, all the indices are the same. N plus I plus 1. So, it makes sense to conjecture that we have a commutative diagram of spaces. Okay, all maps in this diagram are more or less clear. But why does the diagram commute? This time we only have spaces. There aren't any spectra here. We just have xi, xi minus 1, and so on. Any suggestions? How to prove that this diagram commutes? Well, let's formally transform the diagram by removing the sigmas and putting omegas on the right. So okay. Now this diagram clearly commutes. And the question is, how does it follow that this one commutes? Well, now we need to remember that suspension and omega are adjoint functors. So suppose we have this is in fact quite general. Suppose we have two categories, C and D, and a pair of adjoint functors from C to D and the other way around. So we we can form then a diagram like the one shown on the left, and we can also form the diagram so if this is G, then here I put RG, and yes, sorry, W. So these diagrams, if one commutes, then so does the other. And well, as one can observe, these two diagrams are just a particular case of this one. Does this make sense? Okay, so the diagram we want is tricky. We pass by junction to another diagram, and basically this one commutes. There is just one natural map from x I minus 1 to the double loop space of x I plus 1, which follows from the data we're given. Okay. Are there any questions? So we now know that suspension and loop space, which are definitely not equivalences, auto-equivalences of the category of spaces, become auto-equivalences if we pass the spectra. One is the inverse of the other, and sigma is isomorphic to the shift to the left, and omega is isomorphic to the shift to the right. Well, those facts are quite useful. Now we want to well, prove some more facts about spectra. For example, last time we talked about CW spectra and omega spectra, and let's, as an illustration of these notions, let's prove that every spectrum is homotype equivalent to CW spectrum and to omega spectrum. And actually, well, both these assertions follow from what I've already said about the stable model structure. So formally, we don't need those, but actually, one of the ways to prove that we do have a model structure on spectra is by first constructing omega models. So what I propose to do is not 100% superfluous. Well, let's start with the easy part. Every spectrum is homotype equivalent to a CW spectrum. So we start with a spectrum. Well, firstly, let's first assume that instead of just arbitrary spaces, we have polyhedra. This is allowed because we have the singular chain complex, and which in fact comes from the singular simplicial set, and we just take the geometric realization, and then if I apply this to a space, I have a comparison map, and which way does it go? Does it go from X to this thing, or the other way around? Yes, so if X is a space, we have a map from from this very large polyhedron to X, which is in fact a weak equivalence. Very well. It's not. This is not the most economic way to construct polyhedra, but it's basically all we need at the moment. In practice, there's if we need something explicit, this doesn't help, but there are other ways. So this is step one. Step two. We're allowed to further assume that all negative x's are just points. Basically, this procedure does not affect the homotopy groups. And once we have that, we just take the telescopes does the word telescope make any sense?
Like something built from mapping codes?
Yes, it's just the union of the mapping cones along the common spaces which participate in all of those. Just the only thing we need the reduced version of the telescope, meaning we have the base point here, which goes to the base point here, and so on, and we collapse the closed interval, which is which joins all the base points. Okay, so we have this telescope. because we use the reduced version, we have this inclusion. And by the way, I wanted to get rid of the negative x's because here I want to have a finite telescope. Although it doesn't really matter. Oh, sorry, prime. So we get a CW spectrum, and the question is how do I compare this spectrum with the one I started with. Well, the map we want goes from x prime to x, and on the level of the components, it just folds the telescope. And it's more or less straightforward that on each that each square commutes on the nose. So each square strictly commutes, and we get a map of spectra, which clearly induces an isomorphism of the homotopy groups. Are there any questions? So this argument gives us fibrant replacement for spectra. No, the cofibrant replacement. Sorry. With respect to the stable model structure. Okay, so we probably also need the fibrant replacement. Let's see how it works. Okay, so every spectrum is homotype equivalent to an omega spectrum. Okay, so again, suppose we have a spectrum and we want to construct another spectrum, which would be an omega spectrum and which would be homotype equivalent to X, the one we started with. Well, no. Omega j x I plus j. Okay, so what happens here? Well, I have xi goes to omega x I plus 1 goes to omega squared x I plus 2 and so on, and I take the limit as j goes to infinity. Now, what does this actually mean? Well, this actually means the homotypic colimit. If we have a complicated diagram, then actually in topological spaces the homotypic colimits are pretty easy to describe. We just take the cylinders of all maps and glue them together, same as we did for the telescope. And here we actually have another telescope. There's just one subtle thing here. In general, the omegas are not CW complexes, so we need to take the CW approximation of the omegas and then take the telescope. So if we want the result to be to also be a CW spectrum, which would imply it's also cofibrant, not just fibrant. We could replace wall spaces by their CW approximations. For example, by taking the singular subspatial set and the geometric realization, same as we did here. Okay. Now, well, there are two questions. Question one, why do we get a spectrum? And also, why do we get an omega spectrum? So this is what we need to check. Okay, let me start with xi prime. Omega j x I plus j. Okay, omega x I plus 1 prime is the same as omega limit of omega j x I plus 1 plus j. Okay, so now we use a slightly plausible but a slightly technical thing. Recall that in our definition of a spectrum, all spaces were assumed compactly generated Hausdorff. Now, for those spaces, omega commutes with the homotopic co-limits. So let me think a little and see if there is something more general which is worth mentioning here. Okay, so omega is a right adjoint. It does not, in general, commute with colimits. But in this particular case, it does preserve this particular colimit. So I'm allowed to write omega. Sorry, there's a j. Okay, so I is fixed. J is the variable in which we take the limit. So we get j plus 1 x I plus j plus 1. Okay. No, sorry, j. So here we take the limit as j goes to infinity, and here we take the limit as j goes to infinity, but the expressions are exactly the same if we replace this j by j minus 1. So these two spaces are in fact identically the same.
Well, they are not the same, since these homotopy limits, they are just equivalent.
If we take the so if we take the homotopy colimit, then technically this starts at j equal 1, this starts at j equal 0, so they're not, you're right, they're not the same, but they are homotopy equivalent. One of those deformations retracts onto the other. Okay, so we have this this map of the the inclusion from here to here, and this inclusion is an isomorphism in the homotopy category. So here we, I repeat, we have an equality, but it's not for free. Okay, so we have constructed a map from, we have constructed a spectrum. Now the question is, why does this map, why do we get a spectrum which is homotopy equivalent to the one we started with? So we need to show that the spectrum, the two spectra are homotopy equivalent. Now I want to construct a map. and which way will the map go? Okay, from x to x prime. Well, yes, so let's see. This homotopic colimit already contains xi. It also contains all the rest, but it contains, let's see, I have this homotopic colimit. Well, xi is already there. So it makes sense to just map xi to itself as a subcomplex of this telescope. Okay. Now, why does this thing commute with the structure maps? So I have a structure map. And okay, unwinding the definition of omega xi plus 1, I get omega xi plus 1 omega squared xi plus 2, etc., etc. Okay, so this map just does what it does. It's a structure map. Now, by looking at this equality, what does the map of the telescopes do? Well, it's sort of clear what the map of the telescopes does. We have the maps between the components of the one telescope and the other telescope, and all squares commute. So, the map of the telescopes is just the corresponding map of the homotopic colimits. Well, it's clear from this picture that if we use the standard construction of the homotypic colimits for spaces, then this diagram commutes on the nose. Very well. Now, what happens to the homotypic groups? We have a map of spectra. We want to show that this map induces an isomorphism of the homotypic groups. By the way, are there any questions? Okay. So does the map induce an isomorphism of the homotypic groups? Well, let's first remember what the homotypic groups. So Pn of x is the colimit pi n of x is the colimit of x pi n plus I xi. Okay. Let's see. What is pi n of x prime? Well, by the same rationale, it's the limit of pi n plus I of the limit of. So this is as I goes to infinity, as j goes to infinity, omega j x I plus j. Okay, as you know by now, I'm susceptible of messing up the indices, so please check. Well, okay, so again, not for free but true. not for free, but true, I am allowed to swap the pi and the lim. But this time it's actually not very complicated. Here I have a homotopic colimit. And well, the usual compactness type of argument shows that that pi n plus I commutes with homotopic colimits. Oh, sorry, n plus 1, no, I plus j. Okay, so okay, so let me put quotations marks here. And actually, no, without any quotation marks. Let me just say that this thing is the same as pi n plus I plus j x I plus j. So the limits are the same, meaning well, they're not the same, but they look very similar. And it remains to check that and by the way, this if we look closely at this thing, we see that actually the limit as j goes to infinity already suffices. Meaning, let's fix an I and take the limit of this as j goes to infinity. What do we get? We more precisely, let's look at this expression. Let's fix an I. So we fix an I here, and let j go to infinity. Well, it doesn't matter which I fix. I just get the same result for every I. So whatever. Whichever I fix, I get the same limit as here. Very well. But of course, this doesn't quite prove what we're after, because we also need to compare the maps we use to take the colimits. And I would like to leave this as an exercise. Well, there's given what we're given, there's just one possible choice for maps from pi n plus I xi to pi n plus I plus 1 xi plus 1. But still, this is something one needs to check. Okay, so basically it's very similar to the diagram we saw in the very beginning of today's meeting. Are there any questions? Okay, very well. So let's have a break, 20 minutes, and then we'll continue.